All right, welcome to video 6. The focus here is going to be logarithmic functions and their applications. Because it's been a little while since your previous math class, I wanted to spend at least one video with some practice going back through and kind of reminding you what a logarithm is. Not only that, a couple of things from pre-cal, which were laws, being able to go through and solve with exponential and logarithms, because these are things that we're going to do a lot when we start talking about the derivative. And we're going through and finding the slope of the tangent line, and then getting into curve sketching and looking at those kind of applications. So to start, let's look back at the main definition for a logarithm, which is a logarithm is the power to which a base b must be raised to obtain a known number x. So when you're going through and actually solving for a logarithm, the idea is that you're finding a power. That's what your solution and what our logarithm represents. Now, when we write it, starting with the focus of a logarithm, we're looking at it in terms of y is equal to log base b of x. So again, the answer to this expression, whatever y is, it represents the power that x needs to be raised to. So essentially, the power that b needs to be raised to in order to get x. And so this is the equivalent of the exponential form when looking at it. And then we call the previous form the logarithmic form. And so in questions that may be like 2 to the what is equal to 8, I can rewrite this problem in terms of a logarithm by saying log base 2 of 8. What is this equal to? Because again, when I solve this logarithm, the logarithm represents the power that 2 needs to be raised to get 8. In this case, we would say 3, and that would be the solution. Now, when we go through and do this, because we're talking about and really looking at an exponential function, that means my b's are very specific. So my bases that I'm only allowed to look at have to be positive, and b cannot be equal to 1. So when I deal with a logarithm in terms of this base, what this logarithm base is, has to be greater than 0 and cannot be equal to 1. Now, there are two special logarithmic notations that we talked about in previous classes, pre-calculus and algebra 2 specifically, and that is where we have logs with a very, very, very specific base. For example, if I'm talking about a log with a base of 10, we call that the common logarithm, but it is written as just log of x. In other words, if you do not see a power specifically written, and in words I'll say explicitly written, what that understood power is, what that understood base is 10. And again, this is called the common logarithm. You see this key feature in your calculator. If you just hit log, you would be putting in the common logarithm. Now, in using what we talked about last week with the natural number e again is because it's just a number and it can be an exponential base. That means I can also have logarithms that have a base of e. I represent this by using the letters ln, and this stands for natural logarithm, logarithm natural, and that's why it's kind of listed in terms of ln versus nl. Now, ln's, which again are log base e, these are mostly used in theoretical work. So in a lot of math classes, like discrete math, we deal a lot with ln's. It's nicer to look at. It's simpler to look at in terms of instead of having to write log base, 2, 3, 4, 5, whatever, even having to write log, we can cut that down to just an ln. And what we'll find when we talk about derivatives is that the derivative of an ln is simpler than the derivative of a log of any other base. And so we prefer it when we're going through and doing more theoretical work and just talking about theory. But in applications, we can use any type of log. Common logarithm is what you see in most applications in terms of sciences and things like that. All right, so there are a couple of laws, and I left these in just so we could look at them. If m and n are positive numbers, and again, b is greater than 0 and b cannot be 1, then we have the following laws. These laws are always holding true. and they give me in particular the first three ways to condense or expand a single logarithm or expand logs. Sometimes you can hear these referred to as the laws of logarithms, principles, properties of logs. Sometimes they go by a couple different names. Most of the time, though, you'll hear laws of logarithms. And these first three we talked about back in pre-calculus. Again, if I have a single log where there is a product on the inside, then I can express it as two logs of the same base, one containing m, one containing n. But again, the highlight is that if it's a product, we add. If I have a division inside of a logarithm, I can express that as two individual logs with a minus in between. If I have something raised to a power on the inside of a logarithm, I am allowed to bring that power to the front. And then two more properties, and these are things that are always going to hold true no matter what your base is. If you do log base b of 1, you will always get 0. The best way to kind of think about this is by translating it back into its exponential form, which would say b to the 0 is equal to 1. So we can see how that's going to always be true. And then if I do log base b of b, this is always going to be equal to 1 because b to the first power is equal to b. In other words, if I do log base b of b, the only way to get b is if my power is 1. It's the only way. And so this means that log base b of b will always give me 1 as a solution. Now, with these laws and these properties out of the way, we can actually start looking at logarithms as functions. And so I can define them specifically as f of x is equal to log base b of x. Again, b is greater than 0, b cannot be equal to 1. And I can now look at this in terms of inputs and outputs. Now, when I do that, base b has to be fixed. So we do have to define b to be a number. And then my only variables would be the domain and range, what you're allowed to plug in, and then what you would get out of that in terms of its function. Now, because we now have a function, we have multiple representations. This is the equation form. I now want to kind of look at its graph form. Now, we know now that logarithms and exponentials are connected. They're specifically inverses of one another. And we can use the idea of an inverse in order to help us graph. Now, when we, especially me, when I had to go through and sketch logarithms by hand, this is actually the method that we would have to do. Now, I'm just going to talk about it in general, which says that if b is greater than 1, what I'm going to do is graph the exponential. So I know that an exponential goes through 0, 1, and it starts really close to the x-axis, and then increases exponentially. And so this represents the graph of b to the x. Now, every inverse, if I'm graphing it, is a mirror image along the main diagonal, because what an inverse is doing, remember, is swapping all of the x and y coordinates to get the inverse graph. So in other words, if b to the x has a point at 0, 1, this means the inverse, which is log base b of x, must pass through 1, 0. If if an exponential starts really, really close to the x-axis on the negatives, then that means a logarithm is going to start really, really close to the negative y-axis, and then it's going to increase and then flatten out pretty quickly. Essentially, the idea is that if you were to draw a perpendicular line across this main diagonal, all of these pairs of points would just be the swap in terms of their x's and y's. So if I was to pick this point right here, which would be x comma y, this coordinate would be y comma x. It'd be the flip of it. Let me turn my do not disturb on. There we go. All right. So this is the graph of logs. Now we have graphing utilities, so we don't have to worry too much about having to go through and graph an exponential and then graph its logarithm based off of that. We can just go straight to Desmos. We can go straight to, again, using a utility to get its graph. We're going to focus more on what's happening with the graph when we look at its rate of change and its derivative a little bit later. Now this is b is greater than 1. I would encourage you to look at what does the graph for b is greater than 0 but less than 1. So what if it's like 1/2? What would the logarithmic function then look like? And again, maybe try 1/2 as a base. What happens to the graph? I'm going to highlight it, but visually speaking, I would encourage you to go look at it. So let's take a look at some properties then for logarithms, and then some unique properties for e to the x and ln, the natural log. So the logarithmic function y is equal to log base b of x has the following properties. The domain, as we saw in the graph, just scrolling back up, what I'm allowed to plug in for logs are anything from 0 to infinity, where I cannot plug in 0 itself. The reason being is that essentially if you have this scenario here, and I want to know what this is equal to, I am asking what power do I need to raise b by to get 0, and there's no way to do that, right? It's not possible. So I can't get a negative answer, I can't get 0, but I can get everything from that point on. And so thus my domain is 0 to infinity. Now my range, the outcomes that I can get from this is negative infinity to infinity. Again, we see this by the graph because the floor, there is none. It goes all the way down to negative infinity. And although it looks like the logarithm is flattening out, it does continue to increase. Because if we think about the inverse of that, an exponential continues to increase. So when I flip that, it's going to keep going on and on and on. Now a logarithm will always pass through the point 1, 0. It is continuous on the interval from 0 to infinity, so its domain. So there are no vertical asymptotes that we need to worry about. If b is greater than 1, then I'm going to increase from 0 to infinity. But if b is less than 1, I'm actually going to decrease on this interval from 0 to infinity. And so this is what I was talking about. If you graph log with a base of 1/2, where it's less than 1, what you should see is the graph should be decreasing, going from the y-axis onto the right. It's essentially a flip or a reflection of the original graph. All right, now these next two ideas are going to be really important for the examples that we're about to take a look at, because these are the two techniques that we use in calculus and the techniques that we use in theoretical mathematics to go through and solve and simplify expressions, specifically using logs and ln's and using the properties and the ideas and their relationships to one another. For example, you'll see in this first one, if I have e with ln of x as its power, because e and ln are inverses of one another, right? E is the base for this logarithm. Then these two items are going to cancel out because they're inverses. It would leave me with just x. One way, and I'll try to show you this, I didn't really plan on it, so hopefully I don't screw this up. But for this first one, e to the ln x, remember that another way to think about ln of x is log base b of x. And if I'm trying to go through and figure out what this is the same thing as saying, what does e need to be raised to get x as a solution? Well, if I go through and I think about it and try to rewrite it, that answer is going to be just x, when all of this has another e attached to it. Hopefully that kind of makes sense. I feel like that was terrible. So if that was terrible, forget that. And just hopefully that makes sense here. Now, what about the second part? So the second part kind of reverses this idea. It says that if you do the log, natural log of e to the x, again, these two things are inverses, so they cancel each other out, and it would leave me with just an x. For the top one, this is true for x is greater than 0, because again, for a logarithm, I can only use positive values. Here, I can take I can raise e by any number I want. So this means I can use any number I want for x. All right, so I've got pretty much just examples from here on out. You'll see example 1 at the top, example 2 at the bottom. And let's go through, each one of these are essentially solving, and then we'll look at one application type. All right, so solve the equation 2e to the x plus 2 is equal to 5. All right, so I need to go through, and my goal here is I want to solve for the power, what does x need to be, so this exponential will be equal to 5. My whole idea when I solve again is to get x by itself, but because x is located in the power, it's really hard to get rid of that base or to get it rewritten so that we can get x by itself. But Well, it used to be. Now that we know the concept of a logarithm, I can actually go through and do that rewriting fairly straightforward. But it would require me to first get my exponential by itself. So my first step is to divide both sides by 2. So I would get e to the x plus 2 is equal to roughly 2.5, or exactly 2.5. And then now's the part where I need to get rid of the e. Now, from the properties that we just talked about, I can get rid of the e by essentially take the logarithm of both sides. Whatever I do to one side, I need to do to the other. So this would be e x plus 2. This would be ln of 2.5. And on the left-hand side, the ln and e would cancel according to the power we just did, or property that we just did. And whatever's in the power is the solution. It essentially drops down. And then my final answer would require me to subtract 2. And this would be the exact solution. I could use a calculator. Let me go ahead and get that out. I wasn't very prepared. So calculator. All right, and negative 2 plus ln of 2.5. I'm going to get a decimal. It's approximately negative 1.08. And there's my solution. We could check it. You could plug it into the original problem and see if we got 5. All right, for the second one, this is now a logarithmic equation, so we're going to start with an ln instead. And the way that I'm going to solve this is actually still very, very similar to what we just did. So first step is I need to get ln by itself. So I'm just going to rewrite the problem. Okay, so I need to isolate the ln, so then I can isolate my variable. So I'm going to subtract 3. And then I'm going to divide by 5. As a decimal, this is roughly going to be negative 0.6. Now, if I'm trying to get rid of the ln, the opposite of an ln is an exponential of the form e. So what I generally like to do is I actually just go through and I say e the problem. And when I do something like that, notice that the a and ln will cancel and leave me with just x is equal to e to the negative 0.6. And this gives me my exact answer. And if I want my approximate, I get 0.549 as my solution. The decimals go on and on and on, 0.5488116361. This is my solution to example 2. Both of these should be familiar from hopefully Algebra 2 and pre-calculus, but if not, let me know if you have any questions. I'll give you a couple of these just for practice in the attached document. All right, now I got 2 more examples. They're both application type problems, both involving when we modeled with exponentials, because if you recall, from compound interest, we were able to solve for the present value and the accumulated value. But what if I want to know something or solve for the amount of time? Or what if I want to solve for the specific interest rate if I know every other single piece of information? So in this problem, so in applied example 3, how long will it take? So notice that right off the bat, I am looking for time. So I want to know what is t equal to. $10,000 to grow to $15,000. So 10,000, recall, is my principal, and 15,000 is my accumulated value. If the investment earns interest at the rate of 6%, so R is going to be 0.06 per year, compounded quarterly. And remember that compounded quarterly is my N. It's how many times that I'm going through and doing it. And I think we used M in terms of our formula. All right, and so the formula again, just to write it. So A is equal to P, 1 plus R divided by M, and then M times T. And so I'm just going to plug in everything that I know. So I have that 15,000 is equal to 10,000, 1 plus 0.06 divided by 4, times 4t. because again, I don't know what t is. All right, let's go through and let's just kind of simplify some stuff. So I have 15,000 is equal to 10,000 times on the inside. I'm going to do this 1 plus 0.06 divided by 4. The inside here, I get 1.015. And again, this is raised to the 4t. Now, this problem here is exactly the same idea and concept as example 1, where the variable that I'm looking for is in a power. And so I need to get it out of the power by going through and doing and using properties of logs. All right, so the first step is to get this entire exponential piece where my t is by itself. So I need to divide both sides by 10,000. This is going to give me 1.5. Is equal to parentheses 1.015 to the 4t. All right, now what I'm going to do at this stage is I'm going to go through and take the ln of both sides. And I want you to remember property 3, or law 3 of logarithms, which says that if I have a logarithm with a power, I'm allowed to bring that power to the front. So that this right-hand side is really 4t times ln of 1.015. Again, my goal when I'm solving these types of problems is to get the t out of the power, and an ln allows me to do that. All right, so now I want to get this t by itself. So that's going to require me to not only divide by ln of 1.015, but also by 4. So I'm going to take care of that in all one step. So I'm going to do ln of 1.5 divided by 4 ln of 1.015. And this is going to be my t, or how long it's going to take. Let's go ahead and get an approximation for something like this. So ln of 1.5 divided by 4 times ln of 1.015. I get that time would be approximately 6.808, which is really just saying 6 years, pretty close to 7 years for this to grow from 10,000 to 15,000. All right, and the final example, again, we're going to be looking at compound interest. This time, we're going to be looking for the interest rate. So find the interest rate needed for an investment of $10,000 to grow to an amount of $18,000 in 10 years if the interest is compounded monthly. All right, so let's just go through. So again, I'm looking for R. If P is 10,000, to grow to an amount of 18,000. I know time is 10. And then the interest is compounded monthly, so M is 12. Plugging this into my formula, I have 18,000 is equal to 10,000. 1 plus my R, which I don't know, divided by 12. And then in the power, 12 times 10, my M times T. So I'm just going to go through now and kind of simplify a couple of things. Now, I know I'm going to have to divide by the 10,000, so I'm going to go ahead and do that as well. So 18,000 divided by 10,000 is going to give me 1.8. Is equal to, I can't simplify the inside of the parentheses like I did last time because of my variable. I can simplify the power. This would be to the 120. All right, and now I need to get the r by itself, but the r is locked by this exponent of 120. Now, generally, if I'm trying to get rid of this power, we would take a square root, we would take a cube root or a fourth root, but I don't want to take the root of 120. So instead, I'm actually going to incorporate the same rules that we did a little bit beforehand, where what I'm going to do is I'm going to go through and take the ln of both sides in order to get rid of that power. And by getting rid of that power, what I'm referring to is bringing that power down to the front. Now, because my r is locked inside the parentheses, I need to isolate or get rid of that ln. Before I can do that, I need to move this 120 over. So I'm going to do ln of 1.8 divided by 120. This is equal to ln of 1 plus r over 12. And now it's time to get rid of this ln on the right-hand side. Now, to do that, this means that I need to e both sides, or rewrite each side in terms of its exponential. Now, on the right-hand side, those two things are going to directly cancel, leaving me with just 1 plus r over 12. On the left-hand side, this actually would stay as e to whatever this is equal to. So I'm going to go ahead and get a decimal for this. This is ln of 1.8 divided by 120. I get 0.0049. So this means this is an approximation. So I'm going to take care of my equal signs and just put my approximation sign in. And then now I'm just going to walk through and do my normal solve for r. I'm going to subtract 1, and then I'm going to multiply both sides by 12. To do that, I'm going to go through and actually do e to the 0.0049 minus 1. And then I'll multiply both sides by 12. So I'm going to type all this into my calculator. This will give me my approximation for r. So I have 12. To get the e, I do second ln, 0.0049, and then minus 1. So I get 0.0589 for my r. But I want to know r as a percentage. So r is going to be roughly 5.9%, 5.89%, roughly 6% in terms of my percentage for this. All right, so there's going to be some practice here if you need to go through and practice your logarithms. If you feel comfortable with this, then definitely make sure that you are working on your assessment piece for higher order and marginal. If you are completed with that, then make sure if I've gotten it back to you, go ahead and give me feedback on your on my work. And then if you want to, you can look ahead to Friday, which is writing the assessment for exponential functions and compound interest. And so you can start working on that as well if you want to get an early start on that. As normal, check out my virtual class times and check in, or just shoot me an email and we can always do a video chat whenever. And I'd be more than happy to help you. So just let me know. I hope you all have a good rest of your day. See you later.